First, let me start by thanking the organizers for giving me the opportunity to give a talk here. I'll be I'll be talking on a new stochastic Schrodinger-Newton equation, which is closely related to the previous talk that you just heard. Let me start by giving my talk outline. First I'll talk briefly about what is stochastic gravity and why do we need it in the context of measurement problem, and why it gives an insight that there is a fundamental source of decoherence that is present in the space-time structure itself. Secondly, then I will go into the main theme of the talk, which was proposed by Roger Penrose, and also it was given by Professor Diosi. That's the gravitational backreaction in the context of semi-classical gravity. So I will, because you have already heard a lot of talks about semi-classical Einstein's equations, I'll just mention them, and the Schrodinger-Newton equation and its drawbacks, which you have already heard, so there's nothing much to say about it. Then I will talk about model given by Professor Diosi in the context of stochastic gravitational background, and how it can help us in the context of gravitational decoherence, and how it tries to give a resolution towards measurement problem, but not fully. I'll come into it. And lastly is our work on unification of these two ideas, that backreaction due to the self-gravitational potential and the background extrinsic stochastic gravitational field. Lastly, I would conclude with the results that we have got and the further scopes of improvement, which I believe are enough. So first, let me start that why we need stochastic gravity in the first place. So as we have already heard, that the measurement problem is that you don't see superposition for microscopic objects, whereas you see it for massive objects. Sorry, it was the other way around. So you don't see superposition for heavier and massive objects, but you see it for microscopic objects like electrons, protons, etc. So can we say that it has something to do with gravity, because gravity is something that gives you a natural description that it becomes important for massive objects and becomes less and less important when you go to the microscopic regime. So there seems to be a connection, natural connection with this measurement problem and gravity. And also we know that space-time, the background is always there. So whatever measurement is whatever you are measuring, it's in the background space-time, and the wave function propagates through space-time. So it seems very reasonable to think in this line that the stochastic gravity must be important to address such problems. These ideas were put forward by Professor Diosi and Carolee Hazy and Frankel, also Roger Penrose, in the context of semi-classical gravity. So I will not go through all the models, but the basic idea is same, that you have matter which produces gravitational field, and because of the intrinsic, say the Heisenberg's uncertainty principle, there will be fluctuations. So the background space-time will always have a natural and intrinsic space-time fluctuation, which will be can explain naturally the decoherence mechanism that we see in our measurement. So we can see that it can have a connection with the measurement problem that we see around. Okay, so the idea put forward by Penrose was that in the context of semi-classical gravity, of course, that you take a classical background space-time, but your matter field is quantum. So what is so when you consider such a case, then the self-gravity of that object must affect its wave function itself, and then it should come as a nonlinear modification to the Schrodinger equation, which is by itself linear and cannot account for the loss of say loss of superposition. So this is roughly Penrose's hypothesis. So there is, you are already familiar with by now what Schrodinger-Newton equation is. It takes into account the gravitational backreaction by the wave function of the particle itself. And Penrose stated that the final wave function to which the state collapses will be one of the stationary states of this nonlinear Schrodinger-Newton equation. But he has not derived it, so it was just a statement level. And as I have already told that the inclusion of this backreaction term, which is quadratic in the wave function, as I'll show in my later slides, it makes the Schrodinger equation nonlinear. But the problem is that still it is a deterministic equation. So you don't get naturally from such a prescription where the stochastic and random outcomes come in, and how do you get random phases between different states of the particle. And lastly, the statement that was made by Penrose and was later showed by Diosi, that the collapse time will be inversely proportional to the gravitational energy difference between different gravitational states. So this is the framework that we use. This is a semi-classical treatment where background space-time is classical, and I have already said the matter sources are quantum. So you have a semi-classical Einstein equation like this, where this is the expectation value of the energy momentum tensor. So this one again was derived thoroughly in Andre's talk in the school. So you start from a linearized theory of gravity. You take small perturbations around the flat Minkowski space-time. You can derive a gravitational wave-like equation, and you take the non-relativistic limit, and you end up with the Poisson equation, which is given by equation 3. And if you insert the contribution due to this self-gravitational potential into the Schrodinger equation, we end up with what is called a stochastic Schrodinger equation. But as you have already seen that this term, it is not stochastic, it's deterministic. So it cannot give you the decoherence mechanism that we want to explain the measurement problem. So the drawbacks of this hypothesis are already covered in the previous talk. It's I will not go through the points that have already been covered. It's the first faster than light signaling is a problem, and also it's a deterministic equation, as I have said, so it's a problem. But also another thing is because it's highly nonlinear, so it's not exactly solvable. You can solve it numerically and see its behavior, but if you want to do it analytically, you have to make some approximation, some contribution for solving something like that, which we have done. And also because as it was pointed out today by Professor Sudarsky, that it's not compatible with the collapse theory, because there is a non-conservation of energy during collapse, and that contradicts with the semi-classical equation that is shown. So this model has some problems, but let's see how far can we go. Now let me go to another model by Diosi. It's similar model. It's like, because of the quantum matter, you have fluctuations in space-time, and that will affect your Schrodinger equation through this potential. So here phi is the stochastic potential. So here actually in his model, this potential comes with a stochastic contribution. So it can address the issue of decoherence between different possible states, and this has a Gaussian distribution, this noise, and the 2-point correlation is given by equation 6, and this 1 by r minus r prime is due to the gravitational energy. So this was the Diosi-Penrose criterion. The decoherence time is, as I have said, it's inversely proportional to the difference between gravitational energy density. So now our work is to unify these two ideas, because it's very evident from my previous slides that Schrodinger-Newton equation by itself is not sufficient to account for decoherence. So we need to somehow unify these two ideas to take into account the stochasticity of the background space-time. So apart from this self-gravitational attraction, we also need to take account the extrinsic space-time fluctuations that uh, plays a major role in the decoherence of the wave function of a particle. So here we, at the Newtonian level, we add this contribution to the previously known Schrodinger-Newton equation. Now this new term is a stochastic term. Now I will show how this term helps to determine the decoherence time that we can calculate that comes naturally from this kind of stochastic noise due to the space-time fluctuation. So here is a mathematical tool that we use. It's called the phase variance method by Caroly-Hazy. So consider you have a wave function. It evolves like so. The solution, if it's unitary, the solution will be given by something like this: is a free wave function part, and this is a phase due to the stochastic potential. Say, so the stochastic potential is simply given by this. Now what you can do is you can calculate the variance of this stochastic phase between two different points, say R1 and R2. Or if you have a particle, point-like particle, between two different configurations, you can calculate this phase variance. And if it's too large, we say that the coherence is lost and you see decohered states. And so this transition corresponds to what we know as the separation corresponding to this transition, where this becomes of the order of pi square, is what we call as the coherence length, and the corresponding time is decoherence time. So from now on it's pretty straightforward. So you have this potential, which this is the Schrodinger-Newton term, and this is the new term that we have added. Here this small chi is the free wave function, that is without taking into account the non-linearity, because then we cannot do it analytically and becomes highly numerical work. So we wanted to do something like the perturbative approach. So we started with a free wave function solution, and then you can calculate the phase variance between 2 points, any 2 points, say R1, R2. So basically this will be the structure of the phase variance. So because this term is deterministic, this does not contribute to this phase variance, only this part contributes to it. And we already know the 2-point correlation function for this noise, as it was already proposed by Professor Diosi in his earlier works. So now we start with a localized wave packet. So say we consider a wave function localized at the peak of the wave function is at position R1. So the Gaussian wave packet will be given in this form, where A is the width of the Gaussian. So you can calculate using this wave function as the solution of your free wave function. You can calculate the phase difference, phase variance, and the result comes out to be like this, where capital R is the separation between two Gaussians that you have started with. Okay, so this formula is quite difficult then to work with because of this error function. Then we take two limits. For one is for the if the decoherence time is much less than this quantity, then what you get is the result that is given in equation 12. So this is the decoherence time when you have satisfied this condition, or alternatively you can say when you have this condition. So this is for a massive object. If the mass is too large and it's much larger than h cross square g by A is initial width, or say the size of the effective size of your system, then the decoherence time will be given by this formula, and the coherence length is given by this. So here this coherence length is given by the fundamental constants h cross g, and also it depends on the mass and the size of the wave packet, as we can expect. And this result is not very surprising. It was already derived by Professor Diosi in the case of in his model for spherical mass distributions. Yeah, for the other limit, when this decoherence time is very large, we can make some approximations, and then what you end up with is roughly a result integration, the result of this integration is of the order of capital TD R by A, where so this decoherence time for the microscopic objects become like this. So now you have a point-like object whose mass distribution is described by Gaussian wave packets whose width is A and the mass of the particle is m, and you have derived what will be the decoherence time for a microscopic mass, say, or a microscopic mass. So this is what we have got so far. There are some problems and we have to fix it, like to do fully in a non-linear case, taking into account the non-linear it is, and doing it numerically, but we have not done it so far. So this is a analytical result. It matches perfectly well with what was previously known. So this is my last slide. So I have already discussed that we have here unified two different ideas of gravitational self-energy backreaction and the external space-time fluctuation caused by other sources into a same framework. And what we have got from this prescription is we have recovered Dioshi's result for different classical mass distributions. But the issues to be still addressed is that the superluminal signaling is still hanging out there, because the master equation that one will get from this equation is still non-linear in the density matrix. So the superluminal signaling cannot be avoided, and obviously this full nonlinear equation has to be solved using some numerical technique. And this idea is not fully compatible with collapse or the bond. Consequently, the bond probability rule cannot be derived from this. One has to structure this equation in a convenient way, like in a more CSL-like structure, so that one can derive bond probability rule out from the dynamics. And this would be a great thing, because in CSL you have a noise field and you don't really know where it comes from, but if you can somehow connect it to the stochastic gravitational field, then you have a natural source for this noise. So that would be a great thing to achieve. So I would like to thank all, and this is a beautiful campus at TI for Mumbai. Thank you.
Okay, so when you talk about semi-classical gravity, you assume that gravity is classical, gravity can be treated as classical, and the matter component is quantum. I mean, do you treat gravity as fundamentally classical, or is it an effective theory where you can treat gravity classically, but matter component should be considered as a quantum field?
No, for this, to derive Schrodinger Newton, you need to take gravity as fundamentally classical. Otherwise, you won't be able to.
Otherwise, you won't be able to consider collapse, right?
No, otherwise, if your gravity, the space-time is also quantum mechanical, then you won't end up with a nonlinear structure, because everything is linear in that regime, and one can show that the linear, the linear structure comes out from that. You won't be able to account for collapse. So you need, for such a prescription, you need classical background, fundamental classical.
So is it justifiable if someone wants to apply semi-classical gravity in the context of early universe or black hole?
I mean, nobody knows whether gravity is quantum at the fundamental level or not, right? So one is free to treat it as semi-classical gravity. You can say it's an effective theory. Also, you can say that no, gravity is fundamentally classical. Nobody knows. So yeah, it's open. You can.
I would be curious to hear what you think if the mass distribution is uniform, say the wave function is just a constant. Say if you would limit it in a particular volume, whether the collapse would be equally fast as when you have two Gaussians.
are you saying that it's like a state function kind of a thing, like constant in some interval or then in
Yeah, or if you would use periodic coordinates, you could.
No, my question is that whether the mass distribution is, it's uniform throughout the space-time, or it's like a state function. It's constant in a region and then it drops to 0. That's
Yeah, outside it drops to 0.
yeah.
But
Then I
now
would,
instead of having one Gaussian, you have a very broad.
no, I would guess that it won't affect the results because already Professor Diosi has he has done it for spherical mass distribution, where he has already taken into account this kind of mass distribution, uniform in the sphere, and then it drops to 0. So the results won't change.
Thank you.
Any other question?
It's a question either for you and or the previous speaker. I mean, we heard of two theories that sounded superficially similar. They both have a kind of classical gravity. They both have a stochastic component to the gravity. And they both have, I think, some other stochastic field that's driving the collapse and so on. Is that a fair statement? But then in one of them you say there's superluminal signaling, and the other one you say there's no superluminal signaling. So what's the essential difference between the two cases?
For this case, I cannot say about the previous speaker. Yeah, but for this case, because the Schrodinger equation has a nonlinear term, mod psi square, and the combination of the nonlinearity and stochastic term and nonlinear term should be such that it cancels, and at the density matrix level it should give you a linear equation. But the structure of this equation that we have considered is not like that.
I see.
Yeah.
So it's just, is there any way of pointing out a physical difference? I mean, that's just saying you go through the calculation, and I guess in one case you get a linear master equation, in the other case you don't. But can you point to what makes the difference? Or can you point to what makes the difference?
I mean, in our case, it's really because that's what we wanted to get. So we have this quantum feedback picture, the fact that the theory can be rephrased at the mathematical level in orthodox terms, the fact that the flashes, what source the gravitational field, is formally equivalent to measurement outcomes. It's what guarantees linearity. And I guess it's I mean, it's the equations that give this are in essence classified, but it's not all of them. Like you can, yeah, there is so.
Any other question? So if not, let us thank all the speakers of this session.